Assalamu alaikum. Welcome to the next lecture. In this lecture, we're going to start a new topic, and it is the overhead line insulators. So, let us start with the introduction of the insulators. You might have seen and you might have heard about the different types of insulators or about the insulators. So, these are usually the equipments or the supporting uh, or equipments, we can say they are usually the equipments that provide the insulation to the power conductor from the ground. The insulators usually are connected to the cross arm of the supporting structure and the power conductor, which passes through the clamp of the insulator. Usually, power conductor passes through the upper part of the insulator. The insulators are usually made of glazed porcelain or toughened glass. This porcelain contains 20% silica, 30% feldspar, and 50% clay. The dielectric strength of the porcelain it is usually from 15 kV to 17 kV for every 1/10th. That means 0.1 inch of the thickness. So also porcelain is mechanically strong, less affected by temperature, and has minimum leakage problem. Toughened glass also is sometimes used for the insulator because its high dielectric strength, which is 35 kV for 1/10th of the inch thickness, which makes it possible to make use of a single piece construction, whatever may be the operating voltage, because you can see that its dielectric strength is twice as that of the porcelain. Glass being transparent, it is very easy to detect any flaw like trapping of air, etc., or some cracks or other things. It has a lower coefficient of thermal expansion. That means when temperature increases, its expansion is, or it will not expand so much as compared to porcelain. Therefore, the strains due to temperature change are minimized. There will not be any strain due to temperature change. Now, there is one major drawback, that is the moisture condenses very easily on its surface, which makes its dielectric strength to reduce drastically. So, because of this drawback, it is usually limited. Its use is limited up to 33 kV. Nowadays, polymer insulators almost replace all types of insulators because they are lighter in weight. They have the higher tensile strength as compared to the porcelain insulator. Their transportation is very simple. Their performance is better in polluted areas since they are very lighter in weight. They don't have any. They have very less uh, load imposition on the supporting structure. So one more thing, that they are hydrophobic. They require less cleaning action. So this is about the polymer insulators. Now coming back to the porcelain insulator, the design of the insulator is such that the stress due to contraction and the expansion in any part of the insulator should not lead any effect, because due to temperature change, if the temperature increase, it may expand, and if temperature decrease, it may contract. So because of this contraction and expansion, it will not lead any defect to the insulator. So it should be designed on that basis. It is desirable not to allow porcelain to come in direct contact with the hard metal screw thread, because in case of a pin type insulator, we know that we have to insert a pin into the insulator, but that pin should not be in direct contact with the porcelain part of the insulator. Normally, cement is used between metal and porcelain, and the cement does not cause any fracture by expansion or contraction. So that's why we use the cement, which prohibits the fracture due to expansion and contraction. Now let us come to the types of insulator. We have pin type insulator, we have suspension type insulator, we have strain type insulator, we have shackle type insulator, post insulator, guy or stay insulator. This pin type insulator is usually used for 11 to 33 kV, or even this low voltage levels as well, because beyond this 33 kV it will be very costly. And there are other drawbacks for pin type insulator as compared to these type of insulators. Suspension insulators, it is actually made up of a disc insulator which are suspended in case of a straight transmission line where we don't have any bend in the transmission line. We can use the suspension type insulators, or we can say we have a disc, different types of, sorry, more than one disc insulator connected in series. We can say it is a string insulator. The other one is a strain type insulator. It is a similar insulator that we have used in suspension insulator. Only thing is that it is configuration will be different. This is usually connected vertically. This is usually connected horizontal because of the strain of the line. It is used in angle towers when the transmission line is bent. It may be used in dead end, road or river crossing, etc. Wherever there is a strain or net force acting on the transmission line or towers, we use a strain type of insulators. They are actually identical. Only difference will be that their mechanical strength should be more as compared to suspension insulator because they have to bear the strain of the transmission line or tower. We have one more thing, that is shackle type of insulator. This is used in a low voltage system, and it is used as a strain insulator at dead end river crossing or angle towers or angle poles for this low voltage system. Post insulator is it's a type of a pin type of insulator which is used in substations. So it is actually a modular design of pin type insulator where the high voltage post insulator can be made by putting one post insulator on another post insulator. In pin type insulator, such configuration is not available, but post insulator it is available, but it is available where we can use more than one post insulator to be used in the higher voltage level. Guy or stay insulator, it is used between the tie wires to support the poles. When a tie wire is used to support the poles, so to insulate the higher part, that is the uh, top part of the wire from the bottom part, we use a guy insulator in between so as to ensure the safety for the person or other animals. This is the pin type insulator. We have, these are known as petticoats. This is the groove in which the conductor will go from beneath, and a pin can be inserted to this, which is connected to the cross arm, and here we have to connect it conductor. This is the suspension type insulator. These are actually, you can see 1 2 3 4 5 6 7 8 9. These are made of glass here. So these are made of, actually these are the 1 2 3 4 5 6 7 8 9 disc insulators connected in series, and they are suspended from cross arm to the conductor, and here there will be no tension in the transmission line. So strain insulator, again this is the same disc insulator which are connected in series but in a horizontal direction because there will be a net force on this transmission line or on this tower. So to bear that net force, we have to use these type of insulators in this configuration. These are the different shackle insulators for different voltage levels. They are used as strain insulator for low voltage level. This is the post insulator. It is similar to that of the pin insulator. Only thing is that we have some sort of connection at its top and bottom so that we can extend or we can connect other post insulators over this to be used in a higher voltage levels. Now this is the guy or stay insulator. It can be connected like this for upper part of the wire, for lower part of the wire, and they are connected like this so as to isolate the upper part from the lower part. It is used in the tie wires to support the poles. So these are the you can see pictures of the polymer insulators. These you can see these petticoats are made of the polymer, or you can see rubber, just to increase the creepage distance, and this the metal rod is made of the glass fibers to increase the tensile strength and also the dielectric strength. Now coming to the pin type insulator, this is the cross section area of the pin type insulator. These are the petticoats, these two. This is the groove and this is the pin that is inserted over here, and this is the thread of the pin. Pin type insulators consist of a single or multiple shells. Usually we have 2 or 3 shells. These are known as petticoats or range sheds, adapted to be mounted on a spindle to be fixed to the cross arm of the supporting structure. This spindle is to be fixed to the cross arm of the structure, and usually the length of this, or we can say the radius of this petticoat, is usually more as compared to this, or in general the radius of the petticoats which are higher will be more as compared to the radius of the petticoat which are lower. It is because whenever it is also known as rain shed, because whenever the rain occurs, it will only we can say it will only be at the upper part of the petticoat. It will not you can say moist the lower part of the lower petticoats. So that's why it is designed in this way. Multiple shells are provided in order to obtain sufficient leakage of the sufficient length of the leakage path so as to flash over between the power conductor and the pin of the insulator is increased. You can say multiple shells so that this distance, this is known as creepage distance, is increased, so that the flashover voltage is also increased. The design of the shells is such that when the uppermost shell is wet due to the rain, lower shells are dry and provide sufficient leakage resistances. Because due to the rain, the dielectric strength will decrease, because rain itself may be conducting in certain conditions. Since the lower petticoats remains dry, it is capable of still providing a good dielectric strength or leakage resistance. It is desirable that the horizontal distance between the tip of the lowermost shell should be less than as compared to the vertical distance between the same tip and the cross arm. Otherwise, in case of a cross arm, the discharge will take place between the power conductor and the cross arm rather than the power conductor and the pin of the insulator. Thereby, cross arm will have to be replaced rather than insulator. So it means that the length from this center to this center should be less as compared to length from this point to this point. It is because when the flashover occurs, it should occur between this conductor and this pin, so that it will result in the damage of the insulator, rather than if this is more distant than this, there may be possibility that flashover may occur between this and the cross arm, which is placed like this, and cross arm may be damaged. And if we know that cross arm is more costlier than this insulator, so in that case we have to replace the cross arm. The power conductor passes through the groove at the top of the insulator and is tied to the insulator by the annealed wire of the same material as that of the conductor. That is over here. The power conductor is placed over here, and then it is tied to this by the same conductor material from here to here. This groove also is used for the tying the material. Groove is used to place the conductor, and these two grooves are used to tie the conductor to the insulator. The pin type insulator are normally used after 33 kV. In any case, it is not desirable to use them beyond 50 kV, as the cost of such insulators then increase much faster than the voltage. So the cost beyond 50 kV is given by cost is proportional to V raised to power x. So where x is greater than 2, even x is equal to 2, in that case also the cost will be very higher, because for 11 kV maybe the cost is, let us say, 1000 rupees. For 33 kV cost may be 3000, but for 120 it may not be, or 220 it may not be 22,000, it may be more than that, 44,000, 50,000, depending upon the value of the x. So in that case, this is avoided. We don't use this pin type insulator beyond 50 or 33 kV. We go for the other type of insulators. The insulators and the spins should be sufficiently mechanically strong to withstand the resultant force due to combined effect of weight of the conductor, wind pressure, and ice loading, if any, per span length. We know that there's a tension in the conductor, and finally this tension will appear on this insulator. And insulator and pin configuration should be sufficiently mechanically strong to withstand this resultant force. Now the next one is a suspension insulator. The pin type insulators are uneconomical beyond 33 kV operating voltage. Also, replacement of this insulator is expensive, because if this 33 kV insulator is damaged, we have to replace it as a whole, and that will be very costly. But suspension insulator will give us a little bit of reliability, and it will give us different options, and we'll see what are these options. For these reasons, for insulating overhead lines against higher voltages, suspension insulators are used. There's a suspension insulator. Usually it is a special name of the disc insulator where it is used when the transmission line is straight or net force on the tower is zero due to transmission line. And it suspends vertically from the supporting structure to the conductor. These insulators consist of one or more insulator units flexibly connected together and adapted to be hung for cross arm of the supporting structure and carry a power conductor at its lowest extremity. So usually we have, let us say we have only one. Here we are using it or connected it to the cross arm, and here we are using the conductor connected at this point. One more thing, for example, if we use, they are usually designed for 11 kV, one unit, and if we have to use for 33 kV, we have to use 3 units. And if one disk is damaged, we can only replace the 11 kV disk instead of all the whole unit. And in case of pin type insulator, such type of options or such type of flexibility is not there. In that case, we have to replace the whole unit 33 kV pin insulator. Such composed units are known as string insulators because they are combined to form the string of the disc insulators. And in short, they may be also called as string insulators. Each insulator is a single disc-shaped piece of porcelain glued on the undersurface to increase the surface leakage path between the metal cap and the top and the metal pin at the bottom of the insulator. You can see that these are made like this so as to increase the leakage path, or this is known as creepage distance, so that leakage resistance is increased and leakage current is decreased. The cap at the top is recessed so that it can take the pin of the another unit, and in this way a string of any required number of insulators can be built. You can see we have a cap over here. This is the pin over here. This pin may be fit over here of another insulator to make the string of the insulators. The cap and the pin are secured to the insulator by means of a cement. They are finally bound by means of cement. The standard unit is 10-inch cross 5.7. 10 inch is the diameter, 5.7 is the height in size. Suspension insulators being free to swing, the clearance between the power conductor and the supporting structures are more as compared to pin type insulator. This we can say it is disadvantage because they are free to swing along with the conductor. So the clearance between the conductors should be slightly greater as compared to the conductors which are using the pin type insulators, because in that case insulators, pin type insulators are fixed and they are not free to move with conductors due to wind. This means that the length of cross arm of suspension insulator is more as compared to the pin type insulator. The suspension insulators, in addition to be economical as compared to the pin type for voltage more than 33 kV, there are other advantages of the suspension insulators. What are those? Each insulator is designed for 11 kV, and hence for any operating voltage a string of insulators can be used. For example, for 132 kV transmission, the number of insulators required may be 12. It will be the maximum value, because usually you will see that one will be at a voltage of 11 kV and 12 will be at a voltage of, that is 11 12, that is 132. But usually in practice this 132 kV is the line-to-line voltage, and the voltage that appear across the insulator string, that is the phase voltage. So a system with 132 kV system, its phase voltage will be 76 kV, because I have simply divided root 3 to this, it comes out to be 76, or I can take it as 77 kV. So divided by this 11, so we get 7. So actually in actual practice 7 disc insulators are sufficient to bear the voltage of a 132 kV transmission system, because please keep this in mind, It is the phase voltage that appear across the insulator string rather than the line voltage. And for a system voltage, usually three-phase voltage is given. But in general, this is uh, shown in general that 11 kV multiple of 11 kVs for transmission line voltage can be used, and in this case multiple will be 11 into 12. In case of failure of one of the units in string, only that particular unit needs to be replaced rather than the whole string. I have just told you before that for a 33 kV pin insulator has to be replaced as a whole unit, but in case of this we have to replace only one unit of 11 kV. Since the power conductor and the string swing together in case of wind pressure, the mechanical stress at the point of attachment are reduced as compared with the pin type insulator wire because of the rigid nature, then attachment fatigue and the ultimate brittleness of the wire result. In this case, in the pin type insulator, since the pin type is fixed, when the conductor moves, it results in a higher pressure or tension on the insulator. But in this case, since it moves with the conductor, there will be less mechanical stress at the insulator. The operating voltage of the existing transmission line can be increased by simply adding the suitable number of discs in the string instead of replacing all the insulators as necessary in case of pin type insulator. For example, if you have to go from 11 kV to 33 kV, in case of 33 kV, you just have to use other two, increase it by 3. That means you have to use more, 2 discs more, rather than replacing the 11 kV pin type insulator by a 33 kV insulator. So this is one more advantage of it. Now coming to the strain type insulator. The strain insulators are exactly identical in shape with the suspension insulator. They are actually the same type of insulator. Only thing is that they should have more mechanical strength or tensile strength as compared to the suspension insulator. These strings are placed in the horizontal plane rather than the vertical plane, as is done in case of suspension insulators. These are used to take the tension of the conductors at the line terminal, that is the dead end, at angle towers when the transmission line is bent, at road crossing, and at the junction of the overhead line with cables. Junction means when there are more than one uh, transmission line at any pole which are connected to each other. At that time also we use the strain type insulators. These insulators are therefore known as tension or strain insulators because they carry tension as well as strain insulators, so they are used. For low voltage of the order of 11 kV, shackle insulator are used, which I have already told you. But for the higher voltage, string insulator is used. Whenever the tension in the conductor is very high at the long river crossing, etc., sometimes 2, even 3 strings of insulator in parallel are to be used. So when this tension is more, we can use this string type of insulators in parallel to each other so that they share this type of load or this type of tension. Now we'll come to the potential distribution over the string of suspension insulators, and we'll see how this voltage is shared between them. Now the thumb rule for finding the number of insulated discs for a particular operating voltage is to have one disc for every 11 kV. But this does not mean that the voltage across disc of the string is uniformly distributed. This is because of the capacitance formed between the metal parts of the insulator and the tower structures. So when this capacitance is formed, it results in a non-uniform distribution of the voltage across the discs. These capacitance could be made negligibly small by increasing the distance between the insulator and the tower structure, which requires a larger length of cross arm. So we would have neglected, or we would have designed the towers in such a way so that these capacitances are neglected by increasing the cross arm. But practically, if we do that, it results in the increase in the tower width, which increase the cost. So it's not done practically. This will result in the bigger size of the towers, and hence it becomes uneconomical. Therefore, in practice, the insulators are not very far from the tower structure, and hence these capacitance affect the voltage distribution across the string. So we need to see other type of methods which can be used to decrease this type of the non-uniform voltage distribution. The capacitance between each unit, that is between this suspension insulators, that is known as mutual capacitance. So the capacitance between the this insulator and insulator pin and the tower structure that is connected to earth is known as a earth capacitance. Now let us try to see what will happen to the voltage distribution. We have a string of 4 insulators. This actually shows an insulator. It is the upper pin of the insulator. This is the lower pin where the conductor is connected, and this is another insulator because we can. This is pin which is connected to another groove of this pin of this insulator. So we can show that this insulator will behave as a capacitor, and these 4 insulators will be a capacitance which are connected in series. And there will be one more. This is actually a tower structure. The insulator string is connected over here to the tower structure. These capacitance are fictitious capacitance that will appear between the pins of the capacitor, this insulators, and the tower structure which is connected to earth. So let us say this is the mutual capacitance between the uh, mutual capacitance or capacitance of the each string or each disk, that is denoted by MC, and this is denoted by C. It is shown just to have a relationship between these two. We can say this capacitance, since it has some dielectric constant, it will be definitely more as compared to this capacitance. So we can say that this capacitance is more to this capacitance by a factor of M. So when we assume that, uh, in that case, we can see that if this is C, this can be equal to MC. And we assume that all these capacitance of the pin to earth are same. Similarly, all the capacitance, mutual capacitance of the, since they are identical insulators, they are also same. So let M be the mutual capacitance to the capacitance to ground. It will be MC by M. That will be simply M. Here, capacity to the ground is the capacitance of the metal part of the insulated disc to the tower structure that I have told you, that is the pin to the structure. Let the voltage across this be V1, this insulator string be V2, this insulator be V3, and this will be V4. So the total voltage from here to here will be equal to V1 plus V2 plus V3 plus V4. From looking at the structure, you can see that this I1 will be less as compared to I2. Similarly, this I2 will be less as compared to I3. Similarly, this I3 will be less as compared to I4, because this I4 will be equal to I1 plus IC1 plus IC2 plus IC3. I3 will be equal to I1 plus IC1 plus I2, and I2 will be equal to I1 plus IC1. Since the capacitance of these elements are same, and for same frequency, the reactance will also be same. Therefore, the current multiplied by same reactance, you will see this voltage will be more because its current is more. Its current is less. This voltage will be less as compared to this. This voltage will be less as compared to this, and this voltage will be the smaller because it is sharing a less current with the same reactance. So we can say there is a non-uniform distribution of the potential because of these currents. If these currents would have been zero, you will see same current will flow through all the string and same voltage will have will appear across all the disks. But we know that because of these currents, this current is more, so its voltage will be more. Similarly, all the disk will have the lower voltage as compared to this. Now this can be proven also. Let us assume that the voltage, as I have told you, this is V1, this is V2, this is V3, and this is V4. The voltage across this will be the same as that of this. That means the voltage across this capacitance will be V1. Now the voltage across this capacitance, it will not be V2 because this is connected over here and here it is connected to this. So that means this is connected. You can see this is connected between this point and this point. That means the voltage across this capacitance is V1 plus V2. Similarly, the voltage across this capacitance will be V1 plus V2 plus V3. Now, keeping these things in mind, we know that this from this, when we use the KCL at this point, I2 is equal to IC1 plus I1. So I2 is equal to I1 plus IC1. So what is the value of I1? I1 will be equal to V1 into omega MC. V1 into M omega C. Similarly, IC1 will be equal to V1 into omega C. That means voltage multiplied by admittance, voltage multiplied by admittance. Its admittance will be equal to omega MC. its admittance will be equal to omega c. So this will be equal to, its magnitude will be equal to V1 m omega c. This magnitude will be equal to V1 omega c. So what is the value of I2? I2 will be equal to V2 m omega c. So taking common as V1 c and omega, this will be equal to V1 c omega, and I2 will also be equal to V2 m omega c. So cancelling out omega c and omega c, that means V2 is equal to m plus 1 divided by m, that is this. Similarly, writing the KCL equation at point this, that means I3 will be equal to IC2 plus I2. So this is equal to by writing them in admittance and voltage V2 m omega c, and the voltage across this is V1 plus V2 into omega c. That is what it is written over here. So by simplifying over here and putting the value of V2 from this into this equation, we get V3 is equal to V1 m square plus 3m plus 1 divided by m square. Similarly, we can get this V4 in terms of this V1 by first writing the KCL equation and then replacing these currents by voltage and admittance. We get V4 in terms of V1 like this. Normally, as I told you, that this m will be greater than 1 because the capacitance of this will be more as compared to this, because it has its own dielectric strength which has a value greater than 1. So let us take this m is equal to 5. That means when m is equal to 5, this will be equal to 5 plus 1 by 5, that is 6 by 5 V1. This is not minus, this is equal to V3 will be equal to m square plus 3m plus 1 divided by m square. M is 5. This is 25 plus 15, 40 plus 1, 41 by 5. And V4 will be equal to this term plus this term. It will be equal to 41 by 25 plus this. You can see from here, this is 6 by 5, that's 1.2. This is 41 by 2, 25. This is 1.6 around. And this is some more than 2. So in that case, you will see that V4 will be greater than V3 will be greater than V2 will be greater than V1. So which was the conclusion we have earlier made on the basis of the currents. So this means that the voltage drop across the unit nearest to the cross arm is minimum. That is voltage drop across this, and it goes on increasing as we go towards the power conductor. The voltage across this is less as compared to this. This is less as compared to this. Yes, the voltage across this is less compared to this, and the voltage across this is less as compared to this. That means the voltage across the disk which is close to power conductor will be highest, and the voltage across the string or disk which is close to the power structure will be minimum. So it is clear that the lowermost unit in a string of the insulator is fully stressed or utilized. As we go towards the cross arm, the units are less stressed as compared to their capacity, and hence they are not utilized fully. So that means we have to design the insulators in such a way so that the maximum voltage occurs across this, and we have to make it such a way so that its rating should be equal to its maximum voltage appearing. But you will see when we do that and when we use the same identical insulator disk, the voltage across this will be less, the voltage across this will be less, the voltage across this will be still lesser. That means it is utilized fully, but other insulators are not utilized fully for the same voltage level. So string efficiency is a measure of utilization of material in the string and is defined as. So string efficiency will give us an idea of the utilization of the insulators. If string efficiency is less than 100%, it means the utilization is not proper. We're not utilizing it fully. If string efficiency is equal to 100, which is not practically possible, that means there is uniform distribution of the voltage. All the disks are having the same voltage. So it is given by voltage across the string, total voltage across the string. N is the number of insulators in the string, and voltage across the unit nearest the power conductor. So in our case, efficiency will be equal to V, that's the total voltage, divided by 4 into V4 into 100. Since V2 is equal to 6 by 5 V1, V3 is equal to 41 by 25 V1, and V4 is equal to 301 by 125 V1. And total voltage will be equal to summation of these four voltages. It comes out to be 781 by 125 5. When we put all these voltage, that's V here, V4 here, and put their value, it comes out to be 64.867%. You can see that utilization is not proper. In this case, this is more stressed as compared to this. Thank you.